Brian. Okay. Voy a pasar, lo presento. Y listo. Hi, Brian. Are you ready? Okay.
Very good.
We're going to check the audio level. Can you talk something?
Yes, good morning. This is Brian Day, and I am speaking to you from NASA Ames Research Center in California.
Thank you, Brian. Let me show you some of your public today. Okay. And we're going to start. Let me introduce the session. Bienvenidos a todas las sedes. Vamos a dar inicio a la conferencia del día de hoy. Como ya se presentó Brian, él se encuentra en el Ames Research Center. Él es miembro del Instituto Virtual de Exploración e Investigación del Sistema Solar de la NASA. Y hoy nos va a hablar sobre cómo la luz nos sirve para explorar nuestro sistema solar, cómo diferentes tecnologías que aprovechan la luz, diferentes ondas, diferentes longitudes de onda que podemos aprovechar para investigar nuestro sistema solar. Thank you, Brian. That's your turn.
Very good. Thank you very much. So, and I assume, Pedro, you will be advancing through my slides here?
Yes.
Very good. So, good morning, everybody. Thank you for joining me here. We are celebrating the International Year of Light. And as we do so, what I would like to do today is look at how some of our spacecraft use light to explore some of the other worlds in our solar system. So let's move to the next slide. When we talk about light today, we're not going to just talk about visible light, but we're going to talk about the whole band of the electromagnetic spectrum, from radio waves down at the very long end, through microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and then at the very most energetic end, gamma rays. Next slide, please. We're going to start out by talking about one of the great scientists of the early 1800s over in Europe, Auguste Comte. And he did many wonderful things, but he is remembered today not so much for all of the wonderful things that he did, but for something that he got very, very wrong. One of his famous statements is that because the stars are so far away, we would never be able to know what they are made of or how hot they are. Next slide, please. But even as he said this, the discoveries were being made that turned out to make him wrong in that assumption. Because in the 1600s, in 1666, Isaac Newton learned that you can break up light into its rainbow of colors, into its spectrum. In 1828, Joseph Fraunhofer, when he looked at that spectrum, at that rainbow of colors very, very carefully, no, not quite yet, so let's back up one slide, please. Back up one slide, there we go. So in 1828, Joseph Fraunhofer saw that if you look at those rainbow colors very carefully, you will see lines in the spectrum. And those lines actually, we learned in 1859 from Bunsen and Kirchhoff, those lines are actually the fingerprints of the atoms that are being illuminated by that light. And so each atom has its own pattern of colors in that spectrum. And then it works for molecules too, but because molecules are made up of multiple atoms, instead of individual lines, you end up getting bands, whiter bands. But this was very interesting. Okay, so next slide, please. Because this discovery gave birth to the science of spectroscopy. And using spectroscopy, by breaking up the light and looking for these lines and bands in the rainbow of colors, we can then determine the composition, we can measure temperature, we can measure densities, we can measure how fast something is moving toward us or away from us, we can measure how fast something is spinning, we can measure magnetic fields, we can give stars and planets a complete physical exam, even though they are very far away. We don't even have to touch them. And when light is reflected off of rock surface, we look at these bands, these molecular bands, and we can tell what the minerals are that make up that rock. That's a very important concept that we will be exploring more today. So next slide, please. Two of our early explorers in mapping the composition of the moon's surface were two robotic spacecraft, Clementine in 1994 and the Lunar Prospector in 1999. And they had spectrometers on board that studied the surface of the moon to see what minerals were composing the surface of the moon. Next slide. So here is just a photograph of the surface of the moon, a regular photographic image. But now in the next slide, we're going to see that same area, that same view, but through Clementine's ultraviolet and visible light spectrometer, tuned to the lines, the actual molecular fingerprints of iron oxide. And so what we are seeing here is a map, blue being very low concentration, red being high concentration, of deposits of iron on the moon's surface. In the next slide, we see a map from the Lunar Prospector using its gamma ray spectrometer, and again here tuned to the emission or the line of the element thorium. So here we can see how thorium is distributed across the map, the surface of the moon. So we can map out the mineral resources as we look across the moon. This was a great start. In the next slide, we see our next big step in studying the mineralogy of the moon, and that was with an instrument called the Moon Mineralogy Mapper that was developed here in the United States, but then flew on a spacecraft that was launched by India. So this was India's mission to the moon, and again, we are seeing now more and more international cooperation, so different missions will fly instruments from other countries. So on the Chandrayaan mission, the Moon Mineralogy Mapper was flown, and it was able to map the mineralogy in very fine detail for 95% of the moon's surface. Next slide, please. So here you can see, picture on the right shows the surface of the moon, surface detail, and on the left, you are seeing data from 28 different wavelengths that are arranged so that we can figure out the details of all the different minerals that are making up the surface of the moon that we are looking at. Next slide, please. A newer spacecraft called the Lunar Reconnaissance Orbiter, or LRO, is currently in orbit around the moon. And LRO is creating a comprehensive atlas of the surface of the moon. It has a wonderful, wonderful camera that gives us very detailed pictures. It has a laser altimeter that very precisely measures all of the ups and downs. It can peer into dark, permanently shadowed areas. It can measure the temperature on the moon and the radiation on the moon. And it can sniff out deposits of water ice. It's a very exciting spacecraft, and it is orbiting the moon right now. Next slide, please. So I mentioned that LRO has a very good camera on board. And this is a photograph taken from orbit, from outer space, orbiting the moon, and we're looking down at the Apollo 14 landing site. If you look very carefully on the right-hand side, you can actually see the descent stage of the lunar lander. This is what the astronauts rode down to the surface of the moon on. If you look on the left, where that arrow is pointing, you see a little white dot, and that is an instrument package that was left behind by the astronauts. And if you look very carefully in between the white dot and the lander, you'll see some dark squiggly lines. Those are the footprints of the astronauts. So as I said, this is a very, very good camera. Next slide, please. So again, photography is one of the ways that we use light. So we use spectroscopy by breaking it up. We can also use photography to image light. And here's another way we do it. We call it laser altimetry. So again, here is a regular photographic picture of the moon. And in the next slide, you'll see the same area, but now this is mapped by laser altimetry, by bouncing a laser down from a spacecraft down to the surface and waiting for the reflection to come back. And we time the amount of time it takes for the laser light to go down, bounce, and come back. And by timing that, we can measure the distance between the spacecraft and the surface very, very accurately. And as we fly across the moon, we keep bouncing that laser, and we can put together a very detailed map of all the ups and downs on the surface of the moon. Now, it doesn't show up terribly well here, but in the next slide, you'll see how if we color code altitudes, now you can get a much clearer view. In this case, blue is low, green is medium, yellow is higher, and the very highest parts on the moon are coded as red. So you can see here how we get this altitude map of the surface of the moon. Now, it almost looks like the blue areas are water or lakes. That is not the case. That's just how we are coding, how we are identifying different altitudes. Keep that in mind because we'll come back to other examples of this. Next slide, please. Now let's take a look at the poles of the moon, the north and south pole of the moon. And one of the problems we face there is because we are at the poles, the light never shines directly down. The light is always coming in almost horizontally. And so that means craters at the poles of the moon have their floors shaded from the sunlight. There are craters at the poles of the moon whose floors have not seen sunlight in well over 1 billion years. And that makes it very, very hard to plan a mission to the poles of the moon because many of these areas are so dark we can't see what the floor of the craters look like. But in the next slide, you can see how if we use laser altimetry, bouncing that laser down and measuring the time it takes to come back, we can now map the inside of those dark craters. And so all of those dark areas become revealed to us. Next slide. Now, one of the things we are also interested in learning about is the gravity of the moon. Gravity is different than electromagnetic radiation, though. Gravity is not a form of light. But we can use light, we can use electromagnetic radiation to measure gravity. And we did that in a mission called GRAIL, the Gravity Recovery and Interior Laboratory. we had two spacecraft flying together in orbit around the moon. And they had a microwave link between them that they were able to use to very, very accurately measure the separation between the two spacecraft as they flew along. They were able to measure the separation between the two spacecraft to less than a micron. So very, 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 very accurate measurement. But as the two spacecraft would fly along, changes in gravity on the moon would change the separation between the two spacecraft. And by measuring those changes in separation, we were able to measure changes in the gravity as we look at the moon's surface. So on the next slide, we can see, again, here's our photographic view of the moon's surface. And one more slide. Now we see a gravity map view of the moon's surface. And again, the red areas show where there is higher gravity, and blue shows where there is lower gravity. Next slide. Now we can use another part of the electromagnetic spectrum, another area of light, radar, which uses radio waves. Again, instead of bouncing a laser, now we're bouncing radio waves off the surface of the moon. And we can map the surface of the moon with radio waves. The advantage of doing that is that these radio waves can penetrate down into the ground. They can go down 10 to 15 meters. So not only are we able to see the surface, but we're able to look underground and see structures beneath the surface of the moon. Next slide. We're going to see an example of how all of this works. So here is a photograph taken from the Lunar Reconnaissance Orbiter of an area on the surface of the moon called the Marius Hills. And the Marius Hills is one of the most spectacular concentrations of volcanoes on the surface of the moon. So in this picture, you have a very, very spectacular concentration of volcanoes. And as I look at this picture, I don't see much at all. Do any of you see the spectacular volcanoes there? Not so much. But if we switch from a camera view to, in the next slide, our laser altimetry view, there are the volcanoes. So you can see by using a different technique, all those little volcanoes show up. Now let's switch, looking at the same area, to a gravity map view. So here's the gravity map that we can see. And what we are using here is a tool that I will introduce you to, and I hope that you will all use. It is called the Lunar Mapping and Modeling Portal. And one of the things that it allows us to do is stack different views of the moon on top of each other. And as we stack those views, we can adjust the transparency between those views. So you'll see in the next slide, we have adjusted the transparency so that we can see the gravity map, but we can also see the volcanoes beneath. And so what we are doing here is we are looking at the volcanoes on the surface, and with the gravity map, we're looking at this big concentration of lava beneath the ground, beneath the volcanoes there. So we're able to look at the surface and what is beneath the surface. Next slide, please. And one of the things that you can do with the Lunar Mapping and Modeling Portal is you can, when you discover neat things like this, you can actually create a URL bookmark that you can send to your friends, and they just load this into their browser, and they will be able to see the wonderful things that you discover. We'll talk about lunar mapping and modeling in a little bit more in just a bit. Next slide, please. I want to give you another example, and this is how we used spectroscopy to discover water ice on the moon. And we did that with a mission called LCROSS, the Lunar Crater Observation and Sensing Satellite. And LCROSS was a robotic spacecraft that launched to the moon, and as it went to the moon, it carried along with it the upper stage of our moon rocket. Something very big, something about the size of a school bus, a mass of 2 tons. Normally, you throw that upper stage of the rocket away once you have left the Earth. But in this case, we wanted to take it to the moon with us. So as we approached the moon, we turned around and we pointed that upper stage of our moon rocket toward one of those permanently shadowed craters at the south pole of the moon. We released that rocket, and it flew down into that crater at 2.5 kilometers per second, slamming into the ground, blasting many tons of material off the floor of that crater, into the sky of the moon, into the sunlight. And then our little spacecraft dove down into that. So next slide. Here you can see the permanently shadowed floor of the crater Cabeus. And if you look, this picture was taken by the L-Cross spacecraft. If you look very carefully, in the middle of that dark area, in the middle of that shadow, you see that little flash of light there? That is the actual impact of the Centaur upper stage of our moon rocket. That's it hitting the ground, causing that flash. In the next slide, we're again looking at the shadow in the crater Cabeus, but now you see this cloud of dust, this cloud of debris rising up out of the crater. And that is what our spacecraft actually dove down into. And using the spectroscopes on board, we were able to measure the composition, and that's how we discovered water ice on the moon. We blasted that water ice off the floor of the crater, flew through it, and measured it with spectroscopy. Next slide, please. Here we see a temperature map. Remember, using spectroscopy, we can also measure temperatures. And here we're seeing a temperature map that the Lunar Reconnaissance Orbiter, or LRO, made of the pole of the moon. We're looking at the south pole of the moon here. And one of the things that we discovered is that these permanently shadowed craters, these very, very, very dark craters, because they haven't seen sunlight in so long, they are very, very cold. In fact, they are the coldest places that we have measured anywhere in the solar system, even colder than what we measured on the surface of Pluto. So next slide, please. So what we can see is that these permanently shadowed craters are really good places to look for water ice. Any water vapor that is in the lunar atmosphere and the lunar environment will condense there. And not only in those permanently shadowed craters, but even outside of those craters, in areas that do get occasional sunlight, the sunlight is coming in at such a low angle that it does a very poor job of heating the ground. And so even in areas near the poles that get sunlight, we believe that there is permafrost, there is ice beneath the ground, maybe only 10 centimeters down. But we're going to explore that more and find out. Next slide, please. Now, I said something that actually was kind of remarkable. I mentioned the moon's atmosphere. When I was a kid, when I was in school, I learned that the moon does not have an atmosphere. But the moon does have an atmosphere. It's very thin, and we explored it recently with a spacecraft called LADEE, the Lunar Atmosphere and Dust Environment Explorer. And LADEE launched in 2013, and it went into orbit around the moon, and then it dropped down very low, flying through the moon's atmosphere. And again, using spectroscopy, it was able to measure what the moon's atmosphere is made of, what the atmosphere of the moon is, what its structure is, and how those change over time. Next slide, please. So, a lot of what we've seen here is available to you in a tool called the Lunar Mapping and Modeling Portal. So if you go to lmmp.nasa.gov, you can explore the moon as seen through the eyes of many different instruments aboard many different spacecraft. So you can conduct your own exploration of the moon using the data coming back to NASA from our spacecraft. So I encourage you to do that. In our next slide, we're moving on to another world. This is Mars. And Mars is very, very, very fascinating to us right now. If we look in the next slide, we see that Mars, like the Earth, has polar ice caps. In the next slide, we see that Mars has clouds. In the next slide, we see that Mars, as we look at the surface, even has dry riverbeds where water once flowed across the surface of Mars. So we see riverbeds. In the next slide, we see that there are dry lake beds. And in the next slide, we see there are even ancient shorelines. This used to be a beach on Mars. Mars used to be wet, but its surface is very dry now. It is a desert now. But the fact that water once existed on the surface of Mars is fascinating to us, because here on Earth, wherever we find liquid water, even if it's in the boiling pools next to a volcano, or even if it's beneath the frozen ice cap of Antarctica, or even if it's in the cooling system of a nuclear reactor, wherever we find liquid water, we find life. And so if there was liquid water on Mars, we are very, very interested in exploring it. Next slide. So here is a map that was made with a spectroscope aboard an orbiting spacecraft called the Mars Global Surveyor. And this spectroscope was looking at the molecular band, the fingerprint, of a mineral called gray hematite. And gray hematite actually forms in water. So if we see a big deposit of gray hematite, that gives us a clue that this is an area where there was once a lot of water. And so this was used to determine where we were going to send our Mars rover, Opportunity. And if you look in the left-hand portion of this map, you see a dark ellipse, and that is the landing site. That's where we decided to land the Opportunity rover. And when Opportunity explored this area, it did indeed find out that this area was once part of the floor of a Martian sea, that this area was once covered by water. Now let's look at the next slide. And this is one of those laser altimetry maps of the surface of Mars. And here you can see very clearly areas where water once flowed. You can see at the top of the screen river channels. And you can see at the bottom of the screen a large bay that the water flowed into. And if you look very carefully on the floor of that bay, you see structures that were elongated. You can see how they were shaped by the flow of water. So again, that blue is not water itself. That blue in our laser altimetry map shows low areas. But in this case, it's actually showing where water once was. So we can see that Mars, about 3.7 billion years ago, a long time ago, was very, very wet. But then things changed, and Mars lost most of its atmosphere. It became very cold, and much of that water froze. So there's we were not seeing liquid water on the surface of Mars. The surface of Mars became a desert. But even so, in the next slide, as we look carefully, we would see along certain cliffs, we would see fresh-looking gullies. These look very new. And some people thought that perhaps while the surface of Mars might be dry, beneath the surface of Mars, there might still be liquid water. And on these cliff faces, that water might be leaking out and carving these fresh-looking gullies. The next slide, we see something very interesting, these dark streaks called recurring slope lineae. These occur near these gullies where we think water might have flowed. And these dark streaks were first discovered by a college student. He was an undergraduate in 2010, using a very good camera called HiRISE aboard a spacecraft called Mars Reconnaissance Orbiter, or MRO. But the fascinating thing about these dark streaks, these recurring slope lineae, is shown in the next slide. And if you look carefully here, you see how they move, how they change by season. And as we get toward the summertime, the early summertime, they advance down the slope. And recently, next slide please, using a spectrometer called CRISM aboard the Mars Reconnaissance Orbiter, the scientists were able to measure the composition of those dark streaks, and they saw that it was hydrated salts, salt that had been dissolved in water. So what we think is happening here is that salty water is flowing just beneath the surface of Mars. And some of that salty water gets wicked, or kind of soaks up to the surface, and we see it there in these moving dark lines. This was very exciting because last week this was the big announcement of how, for the first time, we are actually now seeing liquid water flowing along and just beneath the surface of Mars. Very exciting for us. So in the next slide, I have an image for you, a movie, and if we click on the movie here, it should run. We get that to, yes. So this is using a tool called Mars Trek that you can use, marstrek.jpl.nasa.gov. And again, this allows you to explore Mars. Here we're looking at a giant canyon called Valles Marineris. This would stretch all the way across North America. Now we can change a view to the laser altimetry view. So we were looking at a photograph, now laser altimetry. Now we will fly down into the canyon. And now we can switch our view to look at this canyon from another instrument on another spacecraft. This is as seen through an infrared spectrometer. So again, this allows you to explore the surface of Mars. And again, the URL is called marstrek, marstrek .jpl.nasa.gov. And just now, as we are speaking, as we are doing this talk, a new addition is being made to Mars Trek. You may have heard of a new story that has come out called The Martian. And in The Martian, we follow the adventures of an astronaut as he travels across the surface of Mars. And in the new version of Mars Trek that just came out today, you will be able to follow the astronaut's path as he journeyed across the surface of Mars. Okay, the next slide, please. This is NASA's Dawn mission. And Dawn is carrying cameras and spectrographs to worlds in the asteroid belt of our solar system. So Dawn visited, as we'll see in the next slide, Dawn visited the asteroid Vesta. On the left, you see a photograph of Vesta. On the upper right, you see the distribution of hydrogen on Vesta. And on the lower right, you see an altitude map of Vesta. And again, using vestatrek.jpl.nasa.gov, you can explore the surface of Vesta. But now the Dawn spacecraft has moved on. It has left Vesta, and as we see in the next slide, it is now at Ceres, a dwarf planet, the largest body in our asteroid belt. And it has just entered orbit there. It is starting to map Ceres, and so we will have a new product soon that will allow you to explore Ceres. The next slide, we will move on to the planet Jupiter. Jupiter is the largest planet in our solar system. If Jupiter were hollow, you would be able to fit over 1,000 Earths inside of it. But what is even more interesting to us right now, in the next slide, are Jupiter's moons. This is Jupiter's moon, Europa. And Europa is completely covered in ice. And this is as imaged by NASA's Galileo spacecraft. But as Galileo flew by Europa and studied Europa, it discovered that beneath that global ice cap, next slide please, we see that Europa has an ocean of liquid water. And again, here on Earth, wherever we find water, we find life. And so if there is an ocean of liquid water on Jupiter's moon, Europa, we cannot help but wonder what might be swimming in there. And so we are planning a new mission to go and study Europa. Next slide, please. Jupiter has two other moons, Ganymede and Callisto, that also have oceans of liquid water beneath their surface. So Jupiter's moons are very interesting to us. In the next slide, we move on to the planet Saturn. And again, Saturn is very beautiful because of its beautiful rings, but also very interesting to us are Saturn's moons. In the next slide, we see an image, a photograph taken of Saturn's moon, Enceladus. And again, Enceladus is completely covered in ice. But if you look carefully, you see there are cracks in that ice. And with our cameras and spectrographs aboard the Cassini spacecraft, in the next slide, we're able to see that there are geysers of liquid water erupting out of those cracks. So we now know that there is indeed an ocean of water beneath the surface, and we are seeing it erupt out into space. We have flown through it. It has even gotten our spacecraft wet. So this is an amazing view. In the next slide, we move on to Saturn's largest moon, Titan. And Titan is unique in our solar system because it is the only moon with a very thick atmosphere. It is 1.5 times more dense. It is 1.5 times thicker than the Earth's atmosphere. It has got a very cloudy surface. But as we use radar from the Cassini spacecraft to look down through those clouds, in the next slide, we see that there are lakes on Titan. But these are not lakes of liquid water. Titan is very, very cold, more than 200 degrees below zero. These are lakes of liquid methane. Very, very cold. But we see lakes on Titan, and then the next slide, we see rivers. So on Titan, The mountains and the rocks are made of water ice, but methane on Titan is very much like water is here on Earth. It can exist in a solid form, in a liquid form, and in a gas form. It rains methane from methane clouds, and then liquid methane flows through rivers into methane lakes. It's a very interesting world. And finally, in the next slide, we see the views that we have recently gotten from NASA's New Horizons spacecraft as it went by the planet Pluto, the dwarf planet Pluto. And here you can see a view of Pluto. In the next slide, we see a close-up view of great big towering mountains. Again, these mountains are made of water ice. And we can tell that because, again, we are using spectroscopy, breaking up the light, to analyze their composition. And in the next slide, we see how there are glaciers of solid nitrogen. And so ice caps and glaciers of nitrogen flowing across the surface of Pluto. And in the next slide, we looking back at Pluto as we have flown past it. Now the sun is behind Pluto, and we can see the sun illuminating, lighting up the atmosphere of Pluto. And again, using the science of spectroscopy, we can see that this atmosphere is mostly nitrogen. So with that, we have reached the end of the talk. I would be glad to try and take any questions that you might have. Thank you.
Thank you, Brian. Thanks a lot for the lecture. Very interesting. Y antes de empezar las preguntas, ¿podemos agradecer la conferencia con un aplauso? Gracias a las diferentes sedes. Vamos a dar inicio a la sesión de preguntas y aprovecho que tengo en pantalla a nuestra escuela de Canadá. ¿Quisieran empezar la ronda de preguntas en Canadá?
Are there any, I mean, water has been something that we've been looking for throughout for a long time. Of course, the next question would be, are there any signs of civilization which we have not found anywhere? Can you comment on that?
So we have not found any signs of civilization anywhere else in space around us, but we are listening. So there's an organization called SETI, the Search for Extraterrestrial Intelligence, that has great big radio telescopes that are scanning the sky, listening for signals from other civilizations. We haven't found anything yet, but space is a very, very, very big place. And so it will take a lot of searching to find it. The search has just begun, but it is continuing as we speak. One of the things, though, that we are very interested in is, since we are finding water now in places like on Mars, now we want to take a look at the rovers that we sent to Mars. In the past, the rovers that we have sent to Mars have been robot geologists that have told us whether or not water once existed on Mars. We now know that it did. And now we know that there is water on Mars just beneath the surface. So now what we want to send is a robot biologist, a rover to go explore Mars and see if there is life there. And so in 2020, we are planning our next rover to go to Mars to actually look for life.
Gracias, Canadá. ¿Alguna otra pregunta o comentario? Another question in Canada?
I have another question about Mars. You say that it was water a long time ago and it was a wet planet like the Earth. I was wondering if our planet, the Earth, it could have the same, in the future, it could become a desert like Mars in the future because of the changing climatation, changing climate. I wonder if we can have the same thing in the future.
Very good question. Could Earth become like Mars? And there are a couple of reasons why Mars suffered this fate. Mars is smaller than the Earth. It is only about 1/2 the diameter of the Earth. It has less mass, and therefore it has less gravity. Because it has less gravity, it was harder for Mars to hold on to its atmosphere. Now, Mars, as we look at the surface, we see that Mars has giant volcanoes. But those volcanoes have all stopped erupting. The age of volcanism, the age of volcanoes, has passed on Mars. And that's important because the volcanoes can pump gas back into the atmosphere. Mars was losing atmosphere, and then as its volcanoes stopped, it stopped adding to its atmosphere. The Earth, however, is much bigger, and so the Earth does a much better job of holding on to its atmosphere. And the Earth's volcanoes, as you well know in Mexico, the Earth has volcanoes that are still very active. And so we are still adding to our atmosphere. But you are very right. Our atmosphere is a very delicate thing. And we see that when we go into space. We think of our atmosphere as being very, very thick. But when we look at it from space, we see we just have this very thin layer of atmosphere on our Earth. And that atmosphere protects us from radiation. It protects us from extremes in temperature. It allows us to breathe. And it protects our resource of water. We have not been doing a very good job of taking care of our atmosphere. I see that here in California when I go to Los Angeles. You see it when you drive around in Ciudad de Mexico. We need to take better care of our atmosphere because as we learn from looking at Mars, an atmosphere is very important. It's what keeps our planet being a place where we can survive.
Gracias, Canadá. ¿Alguna última pregunta en esta ronda?
I guess I should make a statement, well, further comment about this thing of looking for civilization. You probably are very aware that Einstein, one of the things that Einstein said that he knew there were two things that were infinite. One is the universe, and the other is human stupidity. but he wasn't quite sure about the universe.
You know, I have to agree with you.
I must just say that goes it goes in the direction you were talking about, our inability to take care of what we have. In that sense, looking for other civilizations, isn't it a bit like a self-defeating purpose? If we might find another civilization, who says they're not different to us? They might just come and destroy us, you know. Why don't we just lie down low, you know, instead of exposing ourselves to whatever might happen elsewhere?
Well, it is an excellent question, but we have already blown that strategy because we have been very noisy. And as we invented the radio and as we invented television, those signals have spread out across the galaxy. And so now, if there are other civilizations, they will know about us through the novelas that we have been watching.
So Einstein was right.
I'm afraid so.
Gracias, Canadá. Voy a pasar a nuestra siguiente sede. Quiero verificar si en preparatoria 4 hay preguntas o comentarios.
Sí, un momento. Yes, why is there water in Europa Moon?
Can you repeat? Sí, ¿pueden repetir?
Why is there water in Europa Moon?
I'm sorry, I'm having trouble. I've got an echo in that audio. I'm not able to hear what he's saying. Can you help me?
They are asking about the weather in Europe moon.
The weather in Europe?
Yes, and the Jupiter's moon.
Oh, in Europa. So we're talking about Jupiter's moon, Europa?
Yes.
Okay. So Jupiter's moon, Europa, is a very, very different place than the Earth or than our moon. It has an ice cap that covers the entire world. Above that ice cap, there is a very, very, very thin atmosphere, similar to the very thin atmosphere that we have on our moon, not like the thick atmosphere we have on Earth. As a matter of fact, if you were to be standing on that surface of Europa, the atmosphere would be so thin, it would be very similar to what our astronauts experience in the outermost edge of our atmosphere when they do a spacewalk at the International Space Station. So the atmosphere is so thin, it's like being in space. But that's on the surface of that ice cap that covers all of Europa. But beneath that ice cap, there's this ocean of liquid water. And why is there that ocean? It is because of the fact that Jupiter has over 60 moons. And as Europa orbits Jupiter, it also interacts with the gravity from some of these other moons, and it gets squeezed. Tides on Jupiter, or tides from Jupiter, and interactions with the other moons squeeze and stretch Europa. And as it squeezes and stretches, it is heated. And so the hot core of Europa is able to warm the ice that is around it and melt it to form liquid water. That's what we think is going on in Europa. But we want to send a mission there to actually explore Europa in greater detail and help us better understand what is really going on there. Did that answer your question?
¿Alguna otra pregunta o comentario en Prepa 4?
Is it possible to follow astronauts' missions online apart from Mars?
Yes. So it is possible to follow what is going on in our space missions. If you go to www.nasa.gov, you can follow that, and you will see a link for NASA TV, and you will oftentimes see links to be able to see TV broadcasts from the International Space Station. And so as there are astronauts from many different countries that go up to the International Space Station, they will oftentimes have TV programs that will explain to you what they are currently doing on the International Space Station. So again, go to www.nasa.gov and look for the link for NASA TV.
¿Alguna otra pregunta o comentario en Prepa 4?
Thank you.
Thank you.
¿Alguna última pregunta en Prepa 4?
Can you live in Europe moon?
Could we live in Europa? You would not be able to live on the surface because, again, it is very cold. There's a very, very, very thin atmosphere. And Jupiter itself gives off very, very, very harsh radiation. So the surface of Europa is not nice at all. Beneath the surface, beneath that ice, in that ocean, well, we have trouble living underwater, but here on Earth, we have lots of life that is very comfortable living underwater. And so while we might not be able to live very easily on Europa, we think that perhaps other forms of life might be able to live there. And that's why we want to explore it more.
Gracias, Prepa 4. Les pido por favor cerrar su micrófono. Voy a pasar a Colegio Ann Sullivan, verificar si en el Colegio Ann Sullivan hay alguna pregunta o comentario. Si por favor activan su micrófono en Colegio Ann Sullivan. Estamos esperando la activación de su micrófono, Colegio Ann Sullivan. Parece que no hay preguntas. Entonces voy a pasar a la siguiente sede. Voy a verificar si en CCH Naucalpan, quiero verificar si en CCH Naucalpan hay alguna pregunta o comentario.
Sí, tenemos preguntas.
Correcto. Si bajan un poquito el volumen, los escuchamos.
In the future, could be Mars a planet like the Earth?
Oh,
¿Podrían repetir, por favor?
in the
Despacio.
future are you asking if in the future Mars could become like the Earth? Was that the question? Yes. So that is excellent question. That is a process that is called terraforming, and so scientists are looking at ways how if you were to melt some of that frozen water beneath the surface of Mars, perhaps you could end up making Mars's atmosphere thicker again, and thicker to the point where you could actually have liquid water once again flowing across the surface of Mars. And yes, there are ways that could be done. It is not easy. It would be a very big engineering task, but scientists around the world are looking at that and how it could be done. But before we start changing Mars's environment, we need to answer a very important question. Is there already life on Mars? If there is life on Mars there that has adapted to the climate on Mars as it exists today, then we have a moral question. Is it acceptable for us to change the climate on Mars if there is life there that enjoys the current climate on Mars? So before we change the climate on Mars, before we change Mars in a very basic way, it is important for us to learn if there is, in fact, life on Mars.
Gracias.
Great question.
Gracias, SH Naucalpan. ¿Alguna otra pregunta o comentario?
No. Sí, tenemos otra pregunta.
Adelante.
My question is, where is the salty water from the surface coming from?
Si se pueden separar un poquito el micrófono para entenderlo
Where is
mejor.
that salty water coming from? The salty water that's on the surface of the planets.
Can you repeat that for me, Pedro?
Where is the salty water that's on the surface of the planets coming from?
CCH Naucalpan, si se separan un poquito el micrófono de la boca, a lo mejor les entendemos mejor.
My question is, is where the salty water that's on the surface coming from?
Ah, very good, very good. So what seems to have happened is that imagine that Mars was once covered with seas, with oceans. And then as time goes by, those oceans dry up. And so what you are left with is flat plains, flat areas that are covered in salt from those oceans that have dried up. And you have seen salty lake beds here on Earth, where lakes and oceans that have dried up, you can see those salty areas. So on Mars, there are vast stretches of salt. But beneath the ground, we think that there may still be liquid water. So what small amounts of liquid water are still on Mars are probably just beneath the surface. And one of the things that we see with all that salt there on the crust of Mars, when that salt mixes with water, the freezing temperature of that water gets lower. So it is easier to have water be liquid when it is mixed with salt. So you have the water beneath the surface, that ice beneath the surface, it interacts with the salt on the surface, and that lowers its freezing temperature and allows it to become liquid again and to flow. That's what we think is going on there.
Gracias,
Excellent
SH.
question.
Yeah, thank you.
Gracias, SH Naucalpan. Les pido por favor cerrar su micrófono.
Tenemos una pregunta, ministro.
Adelante. Le pido al colegio Ann Sullivan cerrar su micrófono. Creo que ya se resolvió el problema de su micrófono. Les pido en este momento cerrarlo y en un momento regreso con ustedes. Adelante, SH Naucalpan.
Is it possible that...
Sí, adelante, SH Naucalpan.
Is it possible that life on Mars could be able to adapt to the life on Earth, to live here?
That is a very wonderful and very important question. So if there is life on Mars, how do we study it? Do we want to bring it back here to study? And that could be a difficulty. That could be a problem. As we have seen, as we have explored the surface of the Earth, when you have two different types of life that have not experienced each other, that have not met before, oftentimes one type of life becomes the predator and the other type of life becomes the food. And we also found that as explorers moved across the surface of the Earth, and they would bring microbial life with them, bacteria, if you were exposed to bacteria, as they visited a new land, I mean, the history in Mexico is very clear of this. As the European explorers came and visited the New World and landed on the coast of Mexico, and the indigenous people who were living in Mexico were exposed to diseases that they had never experienced before, and there were great epidemics. If we have bacterial life on Mars, do we want to bring that bacteria back here on Earth? Might it survive? That is a question. That is a very good question. So if there's bacterial life on Mars, we need to be very careful about how and where we study it. One of the ideas that has been put forth is, instead of bringing samples back to the Earth, maybe we should bring the samples to a base on the Moon. We could study them there. But if something went wrong and the samples got out, the bacteria got out, the Moon itself is a self-sterilizing environment. The surface of the Moon is very inhospitable to any bacterial life. So maybe that would be the safest way to study life that we bring back from Mars, maybe we study it on the moon. These are questions we have to think very hard about. Excellent question.
Gracias, SH Naucalpan. Les pido por favor cerrar su micrófono. Voy a pasar con Colegio Ann Sullivan. Si activan su micrófono en Colegio Ann Sullivan para preguntas o comentarios.
We are so happy to be part of this conference right here in Mexico. Thank you for giving us a chance. And yeah, certainly we have a couple of questions and we want to thank to the speaker for this great conference. So we will start with the very first question.
Un favor, Colegio Ann Sullivan, si hablan un poquito más despacio.
Hi, my question is, why do you prefer to land on Mars if there's also water in the moon?
Okay. So, yes, we find water on the moon, but the water that we find on the moon is frozen water. We find ice. We do not find, there is no place on the moon is there liquid water. And it is liquid water that we require for life as we know it. So the moon has water in the form of a gas in the atmosphere, and it has water in the form of ice, but there is no liquid water on the moon. That could be a good resource for us as we explore outward, but we do not expect to find life on the moon. But on Mars, where we have an atmosphere, where we have clouds, where we have ice caps, and now we know that there is liquid water, Mars, if we're going to look for life somewhere, Mars and Europa and Ganymede and Enceladus, these are places where there's liquid water, and so we think these are places where there could actually be life.
Thank you.
¿Alguna otra pregunta?
And our very last question would be, have you thought about exploring any other planet besides Mars where you can also find certain characteristics like the ones that you found on Mars?
Yes, so we are looking at a number of places to explore. So Mars is a very good candidate. Again, some of Jupiter's moons are very good candidates. And some of Saturn's moons, Enceladus and Titan. But also we are looking at, for instance, the planet Ceres, or the dwarf planet Ceres. And at the very least, so what we are seeing now is as the Dawn mission explores Ceres, we see that the surface of Ceres seems to be made of clay. And clay is often formed in the presence of water, and we think that beneath the surface of Ceres, beneath that clay, there is ice and possibly even liquid water. So that is another place we would be interested to explore. But then also, it should be pointed out that we are looking at worlds beyond our solar system. We now have things like the Kepler Space Telescope that are exploring worlds beyond our solar system, planets going around other stars. And as we bring bigger and bigger telescopes online, like the James Webb Space Telescope, once that starts flying, we will be able to actually explore the atmosphere of some of these planets going around other stars. And we will be able to look for the signs of life around other worlds going around other stars. Keep in mind the universe is a very, very, very big space. Big place that we think there are, just in our galaxy, there are probably tens of billions of worlds in our galaxy that could possibly support life. So our search is just beginning.
Gracias, Colegio Ann Sullivan. Les pido por favor a todas las sedes cerrar su micrófono. Vamos a las preguntas de Universum.
Hey Brian, are there any plans to use the ice water found on the moon back here on Earth?
So, excellent question. As we find this ice on the moon, we don't really have a need to bring it back here on Earth because we have lots of water here on Earth. But as we decide to move out throughout the solar system and explore the solar system, that ice on the moon could be exceptionally valuable to us. Of course, we're going to need water to drink as we explore in space, and so we can melt that water that we find on the moon and have water to drink, but we can also melt that water and then we can break it apart into its hydrogen and oxygen. We can use the oxygen to breathe, but we can also use the hydrogen and oxygen as rocket fuel, to use that as fuel as we explore beyond the moon. So the moon's water ice resources may enable us to live and work on the moon and to explore beyond the moon, to spread out across the solar system. So the moon's resources are very interesting that way.
Brian, can you tell us about the cost of move different things to the space?
Yeah, so for instance, when we talk about using water, needing water in space, so let's say, I mean, some of you are quite young. Some of you may have your hair is not the color that my hair is. You know, you don't have gray hair like me yet. Don't worry, you'll get there. But some of you may end up having the opportunity to live and work on the moon. But if you're going to live and work on the moon, again, you will absolutely need water. But getting water to the moon is very expensive. If you were to take just a gallon of water from here on Earth and take it to the moon, that costs about 100,000 US dollars for just 1 gallon of water, a couple of liters. That's very expensive to get water from the Earth to the moon. But now that we have discovered all this water ice on the moon, that means that it could be much easier for you to live and work on the moon. That resource is already there. So what we want to do is be able to live off the land, use the resources that are there on the moon, rather than have to bring everything with us from the Earth.
Thank you. We have another question.
Very good.
Yes, thank you. Have you identified what are the bright spots on Ceres?
So those bright spots on Ceres, those have been a big, big mystery. And when we first saw them, people were wondering, what could they be? Could they be geysers of water erupting? Could they be patches of ice? And now our latest information is that they seem to be patches of salt. So again, that tells a story perhaps of water. That maybe at one point there was water beneath the surface and you formed these concentrations of salt, and perhaps that salt was excavated in a crater event as a meteoroid hit, because if you look, those white patches tend to be on the floor of a crater. So we think that there was salt that was exposed in the formation of that crater. That's our best understanding right now. But again, we are just starting to explore Ceres. So this will change. This could change soon. We'll discover more about Ceres, much more about Ceres in the weeks ahead.
Thank you. Another question here.
Thank you. Is it possible to find new elements on these planets?
So the elements that we find are the same elements that we know about. So the periodic table works the same here as it does on Mars, as it does on any of the other worlds. But what we do find is that as we look at elements come in different isotopes, slightly different weights. And the mixture of isotopes is different here on Earth than it is on other worlds. So we find different isotope mixtures as we look in different places of the solar system. That tells us maybe something about how our solar system formed. So while we find the same elements, we find essentially different flavors of the elements as we look in different places throughout the solar system. Great question.
Thank you. And another question.
Hi. I want to know about the NASA summer program.
Okay. So there are internship programs through NASA. And if you go to intern.nasa.gov, that's intern.nasa.gov, you can learn more about that. We have, most of those are for United States students, but we do have something called the NASA Academy. And in the NASA Academy, these are typically college students, and those have international representation. So we have students from many different countries come and you visit a NASA center, and you work with NASA scientists over the summer, and you are given projects to work on. It is a very, very valuable experience. So again, go to intern.nasa.gov and look especially at options for the NASA Academy.
Thank you, Brian. Another question.
Hi, has the NASA found any type of important minerals in other planets?
Yes, so that's an interesting question. Do we find any important minerals on other planets? And the answer is yes. So for instance, here on Earth, we have a set of elements that we call the rare earth elements. And rare earth elements are very important. We use them in many electronics. Many of our, your cell phone depends on having rare earth elements. So, they're the magnets that are in your cell phone that make it work are typically rare earth element magnets. But rare earth elements are not very easy to find. You just find them in certain places here in high concentrations on the Earth. But on the moon, we find that there are large areas that are enriched in rare earth elements. Again, as we start moving through space, what we'll want to do is find the resources out there rather than bring everything with us. So there are companies here on Earth that are looking at how we can get the resources we need in space rather than trying to bring everything from the Earth. But there may even be some resources that we find in space that would be worth bringing back to Earth, and perhaps the rare earth elements might be among them.
Thank you, Brian. Vamos a una última ronda de preguntas. Voy a empezar por CCH Naucalpan. Quiero verificar si en CCH Naucalpan hay alguna última pregunta.
No, pero ya terminamos con las preguntas.
Gracias, CCH Naucalpan. Voy a pasar a Preparatoria 4, verificar si en Prepa 4 hay alguna última pregunta o comentario.
Know if it's possible to live in another planet, and if what's the classification of Europa?
Could you repeat that for me, Pedro?
Let me check because I didn't understand. Si repiten, por favor, un poquito despacio.
If it's possible to live in another planet, and the classification of Europa?
Still do not understand. I have a big echo on that, Pedro. Were you able to hear the question?
¿Podrían repetir la pregunta en español para transmitirla a Brian? Prepa 4, ¿podrían repetir la pregunta en español para repetirla a Brian?
Que si es posible la vida en otro planeta y la clasificación que tendría Europa.
Sí, la clasificación, no entendí a qué se refiere. Si me aclaran un poquito la pregunta sobre la clasificación de Europa.
Bueno, solo la primera pregunta.
Correcto. Brian, they are asking,
I'm not hearing you, Pedro.
just give me a minute.
Okay.
Solo la primera, I guess. In this research, have you been found evidence of life in other planets?
We have not found evidence of life yet. We have found organic chemicals. We find the building blocks of life. We see in rocks we get from space, we see amino acids that are the building blocks of protein. We see nucleotides that are the building blocks of DNA. So we know that all the chemistry that we need for life is out there. And we now know that there are certain places where there's liquid water, which we understand is necessary for life as we know it. So the time has come for us to not just send robot geologists to these other worlds, but now to send robot biologists, because some of the basic things we need for life we now know are there. So it is time to look for life itself. We haven't found it yet, but we're just starting to look right now.
Gracias. Thank you, Brian. ¿Alguna otra pregunta en Canadá? Quiero verificar si Canadá sigue enlazado y si hay alguna pregunta o comentario final. Creo.
Looks like they are gone.
Yes, I think so. Aquí una última pregunta. Sí, the final question.
Do you think if it's possible in the next 50 years to establish a colony in Mars?
So our plan is to have humans go to Mars, certainly within that time. In terms of how long, what kind of presence we will have there, will it be a permanent presence? Will people be actually living on Mars? We're not sure yet. There are certainly people who are working toward that. There's an organization called the Mars Society, and there are a number of organizations that are working toward having long-term human presence on Mars. Will we be there in the next 50 years? I don't know. We are certainly working in that direction, but it takes a lot of money to do something like that. And so in order for that to happen, it probably won't just be one country that is doing it. It will be multiple countries cooperating with each other. And I think that's going to become more and more important as we become more and more ambitious about what we do in space. And so that is why I am very much looking forward to further talks between our space agency, between NASA and the Agencia Espacial Mexicana, because it is going to be necessary for countries to work together to do these great things. And so I have had early talks with the agency there in Mexico, And I am looking forward to further talks because I think a partnership is going to be essential if we're going to move ahead. We're going to have to do this as an international effort, as the human race moving into space altogether. Thank you very much.
Thank you, Brian. Have you noticed we are exactly on time to finish?
Amazing. Very impressive.
Thanks a lot, Brian. Gracias a las sedes que nos acompañaron. Gracias, Brian.
Gracias. Muchas gracias.
See you soon, I hope.
Very good. Hasta la vista. Bye.
Gracias a las sedes que nos acompañaron. Terminamos la sesión del día de hoy.